Ever wondered what happens when you try to merge quantum mechanics with general relativity? Unlike other theories that treat gravity as a mysterious force, loop quantum gravity builds on Einstein's geometric description of spacetime. First, we have the more traditional canonical loop quantum gravity. This approach focuses on the mathematical description of quantum space and is a bit more conservative in its assumptions. On the other hand, we have covariant loop quantum gravity, also known as spin foam theory, but it doesn't stop there. LQG has given birth to an even more intriguing subfield called Loop Quantum Cosmology. This theory takes the principles of loop quantum gravity and applies them to the entire universe. One of the most exciting ideas in LQC is the concept of the Big Bounce. Imagine the Big Bang not as a singular event, but as a transition from a prior period of contraction, known as the Big Crunch. Instead of a universe that pops into existence from nothing, it bounces back from a previous state. We will jump into each and every tiny bit of the details. If you're as intrigued as I am, hit that subscribe button, and here we start our journey. What does it mean for a theory to be background independent? Simply put, in loop quantum gravity, the equations are not embedded in or dependent on a pre-existing space and time framework. Instead, they are expected to give rise to space and time at distances which are around 10 times the Planck length. In most traditional theories, space-time acts as a stage where physical events unfold. But in loop quantum gravity, space-time itself is a dynamic entity that emerges from the interactions of quantum fields. This concept is known as the relationalist interpretation of space-time. Essentially, space-time is not a container for the universe, but one of the fields forming the world, just like any other force or particle. This leads us to an important symmetry in loop quantum gravity, which is invariance under diffeomorphisms. In simpler terms, the physical laws remain unchanged, even when we reshape our coordinate system. For spatial diffeomorphisms, this is well understood. However, when it comes to diffeomorphisms involving time, things get a bit more complicated. This brings us to what's known as the Hamiltonian constraint, a subtle issue related to the dynamics of spacetime and the problem of time in general relativity. Currently, a universally accepted framework to account for this constraint is still elusive. However, a promising candidate is the operator introduced by physicist Thomas Thiemann. His work provides a potential pathway to resolving these complex issues, though much research is still needed. In between all this, we have the loop representation. This approach involves describing the quantum state of the gravitational field using loops, which are mathematical constructs that can capture the geometry of space in a unique way. In detail, the loop representation leverages the concept of holonomies, which are path-dependent transformations that provide a way to encode the curvature and connection properties of space. These holonomies are closely related to Wilson loops, which are used in gauge theories to understand the behavior of fields over closed loops. Furthermore, the loop representation introduces knot invariants, mathematical entities that remain unchanged under certain transformations of loops. Now let's delve into another crucial aspect called the Hamiltonian constraint in loop quantum gravity. In the long history of canonical quantum gravity, formulating the Hamiltonian constraint as a quantum operator, known as the Wheeler-DeWitt equation, has been a formidable challenge. However, it was within the loop representation that a mathematically well-defined Hamiltonian constraint was finally formulated in 1996. The Hamiltonian constraint, along with the quantum versions of Gauss's law and spatial diffeomorphism constraints written in the loop representation, form the central equations of loop quantum gravity. The primary technical goal of loop quantum gravity is to identify the states that are annihilated by these constraints, known as the physical states, and to determine the corresponding physical inner product and observables. One fascinating aspect of the Hamiltonian operator is that it only acts at vertices. More precisely, its action is non-zero on vertices with a valence of 3 or greater, resulting in a linear combination of new spin networks. But what is the semiclassical limit? The semiclassical limit is the ability of a physical theory to approximate classical mechanics. In essence, any candidate theory of quantum gravity must be able to reproduce Einstein's theory of general relativity as a classical limit of a quantum theory. However, achieving this is no small feat. Quantum field theories have different sectors, analogous to the various phases in statistical systems. Just as these phases are physically distinct, so are the different sectors of a quantum field theory. This means that loop quantum gravity may belong to a sector where general relativity is not recovered in the semi-classical limit. Alternatively, there might not be any physical sector at all. However, if loop quantum gravity fails to have the correct semi-classical limit, these theorems would spell the end of the loop representation of quantum gravity. There are several difficulties in establishing that loop quantum gravity gives Einstein's theory of general relativity in the semi-classical limit. For instance, there is no operator corresponding to infinitesimal spatial diffeomorphisms in loop quantum gravity, as the theory predicts. Spatial geometry has a discrete nature. This issue can be circumvented with the introduction of the master constraint. Additionally, reconciling the discrete combinatorial nature of quantum states with the continuous fields of the classical theory presents a significant challenge. The algebra of Hamiltonian constraints doesn't close, but the master constraint improves the situation. The semi-classical machinery developed so far is only suitable for non-graph-changing operators, while Thiemann's Hamiltonian constraint is a graph-changing operator. Time to talk about black hole thermodynamics. This field seeks to reconcile the laws of thermodynamics with the existence of black hole event horizons. The no-hair conjecture of general relativity states that a black hole is characterized only by its mass, its charge, and its angular momentum. Hence, it has no entropy. At first glance, this seems to suggest that one could violate the second law of thermodynamics by dropping an object with non-zero entropy into a black hole. However, groundbreaking work by Stephen Hawking and Jacob Bekenstein showed that the second law of thermodynamics can be preserved by assigning to each black hole a black hole entropy. An important oversight in the application of the no-hair theorem is the assumption that the relevant degrees of freedom accounting for the entropy of the black hole must be classical in nature. But what if they were purely quantum mechanical instead and had non-zero entropy? This is precisely what is realized in the loop quantum gravity derivation of black hole entropy. Due to its background independence, loop quantum gravity allows for a classical black hole spacetime to emerge from the semi-classical limit of the quantum state of the gravitational field. However, there are many quantum states that share the same semi-classical limit. Specifically, in loop quantum gravity, it is possible to associate a quantum geometrical interpretation to the microstates. From the covariant formulation of the full quantum theory, known as spin foam, it is possible to derive the correct relation between energy and area, known as the first law of black hole thermodynamics. Additionally, the Unruh temperature and the distribution that yields Hawking entropy can be derived. This calculation utilizes the notion of a dynamical horizon and is applicable to non-extremal black holes. Now let's delve into another captivating topic known as Hawking radiation in loop quantum gravity. How does this phenomenon fit into the framework of loop quantum gravity? A detailed study of the quantum geometry of a black hole horizon has been made using loop quantum gravity. Interestingly, loop quantization does not reproduce the exact result for black hole entropy originally discovered by Bekenstein and Hawking. Unless, of course, one chooses the value of the Emitsi parameter to cancel out another constant that arises in the derivation. Based on the fluctuations of the horizon area, a quantum black hole exhibits deviations from the Hawking spectrum that would be observable if X-rays from Hawking radiation of evaporating primordial black holes were detected. These quantum effects are centered at a set of discrete and unblended frequencies, highly pronounced on top of the Hawking radiation spectrum. Now let's turn our attention to an even more intriguing concept, which is called Planck stars. In 2014, physicists Carlo Rovelli and Francesca Vidotto proposed an innovative idea that has sparked significant interest in the scientific community. They suggested that within every black hole lies a Planck star. But what exactly is a Planck star? According to loop quantum gravity, as a star collapses to form a black hole, the energy density at its core reaches an extreme level, known as the Planck energy density. When this critical threshold is reached, a repulsive quantum force is generated, preventing the star from collapsing into a singularity. Instead, it forms a Planck star at its core. For one, it offers a potential solution to the black hole firewall paradox, which posits that an observer falling into a black hole would encounter a wall of high-energy particles. The existence of a Planck star could mean that the interior of the black hole is not as hostile as previously thought. Additionally, this concept addresses the black hole information paradox. Traditional theories suggest that information is lost forever when it crosses the event horizon of a black hole, challenging the principles of quantum mechanics. However, if a Planck star exists, it could store and eventually release this information, preserving the fundamental tenets of quantum theory. Loop Quantum Cosmology is an extension of loop quantum gravity that applies its principles to the entire universe. Traditional cosmology suggests that the universe began with a singularity known as the Big Bang. However, Loop Quantum Cosmology offers an alternative narrative. According to Loop Quantum Cosmology, instead of a singularity, the universe undergoes a quantum bridge between contracting and expanding phases, leading to what is known as the Big Bounce. This means that before the Big Bang, there was a previous contracting universe that, upon reaching a critical density, rebounded to form our current expanding universe. By applying the principles of loop quantum gravity, it provides a framework where the singularity is avoided and the universe transitions smoothly through the Big Bounce. Moreover, Loop Quantum Cosmology presents a natural mechanism for cosmic inflation, the rapid expansion of the universe shortly after the Big Bang. In some quantum theories of gravity, a spin-2 quantum field is quantized, giving rise to theoretical particles known as gravitons. In string theory, these gravitons are described as excitations on a classically fixed background, making the theory inherently background-dependent. This background dependence can have profound physical implications, such as determining the number of quark generations. However, loop quantum gravity, like general relativity, is fundamentally background-independent. It eliminates the need for a predefined background, unlike string theory. Interestingly, while loop quantum gravity does not introduce gravitons as building blocks, it is anticipated that in a semi-classical or weak field limit, something akin to gravitons may emerge. Moreover, loop quantum gravity is formulated in 3 and 4 dimensions and does not require supersymmetry or Kaluza-Klein extra dimensions, unlike string theory. This difference has led some physicists like Carlo Rovelli to argue that loop quantum gravity's formulation is more parsimonious and consistent with current experimental results. Despite these differences, both theories seek to overcome the non-renormalizable divergences of quantum field theories. Many of the challenges in physics today are theoretical, meaning our existing theories struggle to explain certain phenomena or experimental results. Others are experimental, where the difficulty lies in creating an experiment to test a proposed theory or investigate a phenomenon in greater detail. Loop quantum gravity is not exempt from these challenges. Some of the critical questions it faces include: can quantum mechanics and general relativity be unified into a fully consistent theory, perhaps as a quantum field theory? Is space-time fundamentally continuous or discrete? Would a consistent theory involve a force mediated by a hypothetical graviton, or would it emerge from a discrete structure of space-time itself, as loop quantum gravity suggests? Are there deviations from the predictions of general relativity at extremely small or large scales, or in other extreme circumstances that could be explained by a quantum gravity theory?